Okay, so next up, let's briefly review solubility. Now, a saying in chemistry that we use with solubility is that like dissolves like. What that means is that, so i.e., that means that polar stuff dissolves in polar stuff, and nonpolar stuff dissolves in nonpolar stuff. So polar in polar, and nonpolar in nonpolar. So a couple of other vocabulary words that we need to know are solute and solvent. So solute is the stuff that's being dissolved, and the solvent is the stuff that's doing the dissolving. So the solute is what's present in the lesser amount, and the solvent is what's present in the greater amount. So like if we took, for example, some table salt, so here's my table salt, and we mixed it with water, then the table salt would be the solute and the water would be the solvent. Now, the word that we use to describe when the solute mixes with the solvent and forms a homogeneous mixture is soluble. So, most organic compounds, and so organic compounds we're going to learn that's stuff that contains carbon, so stuff with carbon. Most organic compounds are soluble in organic solvents. The reason for this is that in organic compounds, we always, like by definition for it to be organic, it always is going to have one or more carbons, and probably also some hydrogens as well. And so we know that carbon-carbon bonds and carbon-hydrogen bonds are non-polar. And so if we have a bunch of carbons and a bunch of hydrogens, which is usually the case with organic compounds, there is going to be enough of it that is non-polar, that, like, even if we classify the compound as polar overall, there's enough of it that's nonpolar that makes it mix. But the easy way to remember this is just you look for, if you're trying to figure out if an organic compound is soluble in another organic compound, the answer is almost always yes. Okay, so then the question is, well, if organic compounds, so like organic solutes, are almost always soluble in organic solvents, then, well, what are they not soluble in? And so this is where we get, where we have to think a little bit more closely about intermolecular forces, because we know that the most common solvent is water, right? Like water, in the ocean and like all over the place in our bodies. It's a really, really, really common solvent. So for the most part, even though we care about the solubility of organic compounds in other organic compounds, we care a little bit more about the solubility of organic compounds in water. So what these next two options are going to look at is the solubility in water. Okay, so nonpolar organic compounds are going to be insoluble in water. So insoluble, meaning they don't dissolve. So insoluble in water. The reason for this is that water is super, super, super polar, right? It has tons of hydrogen bonding. It's super, super polar. And so if we have a nonpolar organic compound, then that's like nonpolar is not going to mix with polar because like our solubility thing is like dissolves like. Okay. Polar organic compounds, you might think that they would just like automatically be soluble in water because, right, polar mixes with polar. However, that's not always the case. It has to meet certain criterion for it to be soluble in water. So a polar organic compound is going to be soluble in water. So I'm going to write water soluble only if they are small. So we're talking like probably less than like 4 carbons. Anyway, so if they're small and they contain, now pay special attention to this, they contain an oxygen, a nitrogen, or a fluorine. So where else have you heard of oxygen, nitrogen, and fluorine being grouped together, aside from like on the periodic table? Well, it's in hydrogen bonding. And so the ability of small organic compounds to dissolve in water has to do with their ability to hydrogen bond with water. So, if it contains an O, an N, or an F, it is able to hydrogen bond with water. Now, I also want you to notice that it says in here, and it's correct, that it has to contain an O, an N, or an F. Notice that it does not say that it has to contain a hydrogen connected to an O, an N, or an F. And that is because for hydrogen bonding to occur, remember, I'm going to go back a few slides, only one of the molecules has to have an NH, an OH, or an FH, and the other molecule has to have an O, an N, or an F. And so when we're talking about something hydrogen bonding with water, well, water already has that OH. And so for something to hydrogen bond with water, the other molecule that's hydrogen bonding with it, it just has to have an O, an N, or an F. Okay, so let's do a couple of examples where we're predicting the solubility of something in something else. So examples. Notice that here you're given the structures of them. I know that I haven't introduced you yet to like what these structures mean and how they're drawn. We'll get to that, but I think that you can probably figure it out just by like what's polar and what's nonpolar just by looking at the atoms that are part of it. So hexane, it has 1, 2, 3, 4, 5, 6 carbons and a whole bunch of hydrogens. So only having carbon-carbon bonds and carbon-hydrogen bonds, and all of those bonds being nonpolar, hexane is going to be nonpolar overall. So ethanol, notice that it has 2 carbons, but it also has an oxygen and a hydrogen. And so having that oxygen and the hydrogen, we could go through and look and see if there's like an uneven distribution of charge. I'm just telling you right now, there is an uneven distribution of charge. We'll get to how to tell that more easily for organic compounds. But just right now, I want you to understand that yes, it is classified as a polar compound. Okay, so this is polar. And so let's predict their relative solubilities, just predict their solubilities in, first off, an organic solvent. So to see if something is soluble in an organic solvent, we ask, okay, is it an organic compound, right? Because if it's an organic compound, usually it's nonpolar enough that it will be soluble in an organic solvent. Okay, so since both of these are organic compounds, right, they both have carbons, then they are both going to be soluble in an organic solvent. And so remember that like this one is the easier one, just because we think, okay, we look and say, okay, is it organic? Then yes, it's probably going to be soluble in an organic solvent. The trickier one that we have to look at is solubility in water, because again, water is so common. It's a really, really, really widely used solvent that we care about. It's about something's solubility in water. We also care about this in medicine because, like, right, our bodies have lots and lots of water in it. So it's going to be important to predict the solubility of medications, like, in blood versus like in fat, for example. Okay, so then to figure out if each of these is going to be soluble in water, we are going to ask, okay, is it small and does it contain an oxygen, nitrogen, or fluorine? Well, this one, it looks kind of big to me. I mean, 6 carbons, that's a lot of carbons. So additionally, it does not contain an oxygen, a nitrogen, or a fluorine. So this, I'm going to guess, is insoluble in water. And sure enough, if we did an experiment of this, if we took hexane and water, they're both liquids at room temperature, and we mix them together, we would find that no matter how much we shook them, it would always separate out into 2 layers, like with oil and water, where like hexane would be kind of like the oil. Okay, ethanol. So we ask, all right, is it polar? Yes, we decided that it's probably going to be polar. It has that oxygen in there. And is it small? Okay, yes, it's fairly small. It only has 2 carbons. And does it contain an oxygen, a nitrogen, or a fluorine? That, again, can hydrogen with water. The answer for that is yes. So we would guess that ethanol would be soluble in water. And sure enough, ethanol is definitely soluble in water. Ethanol is the chemical name for like alcohol that is like a component of, wine and beer and vodka and all that stuff. And it would be very, very difficult to find something that is 100% ethanol. So usually, well, I think actually I'm going to say always, if you drink something that has alcohol in it, it's going to be a mixture of ethanol and water. And ethanol's ability to dissolve in water has everything to do with its structure and with its intermolecular forces. Okay, so why is this exactly? Like, why does polar dissolve in polar and nonpolar dissolve in nonpolar? Well, the way that I like to think of it is that molecules that have the same intermolecular forces, that's abbreviated just IMFs, molecules with the same intermolecular forces like to mix. And when I say like to mix, that really should be like in quotation marks, because, like molecules don't have feelings, they don't like or dislike anything. But in nature and in science and chemistry, nature is always trending toward a lower state of energy overall. So when we have molecules that have the same intermolecular forces, mixing together is the lowest in energy. Okay, so for example, why is CCl4 not soluble in water? Well, first off, let's look and see that CCl4, even though it has individual polar bonds, overall the molecule is nonpolar. So that's one hit against it. It's nonpolar. It's small, but it's nonpolar, and it doesn't have an oxygen, a nitrogen, or a fluorine that can hydrogen bond with the water. So when you introduce, let's just say, a single molecule of CCl4, carbon tetrachloride, to water, you have these two water molecules that are attracted to each other. There's, the strong partial positive on the hydrogen and the strong partial negative on the oxygen. And so they have a strong attraction to each other. And so if the CCl4 comes in and tries to break that interaction, it can't really do it because it would interrupt those favorable strong interactions and only be able to replace them with London dispersion forces, which we know are not as strong as hydrogen bonding. Okay, so let's look at another example. So why is methanol soluble in water? First off, I'm going to add some lone pairs here. Missed those. Okay, so then let's look at water again. So, two water molecules interacting again. So we have partial positive on the hydrogens and a partial negative on the oxygens. And so they're happy and hydrogen bonding with each other. Okay, so as this methanol molecule approaches the two water molecules, it is able to disrupt that hydrogen bonding. It interrupts the hydrogen bonding. However, in interrupting it, it's able to form new hydrogen bonding interactions, right? So we have a new hydrogen bond between this oxygen and this hydrogen from one water, and then maybe this hydrogen and this oxygen from the other water. So in summary, the CH3OH, that's the methanol, it interrupts, but it forms comparable, favorable, strong interactions. So even though it interrupts the hydrogen bonding, it's able to form new hydrogen bonding. And that's why we say that like dissolves like. That polar dissolves in polar, nonpolar dissolves in nonpolar, and specifically why that's how that can be applied to water. To stuff dissolving in water. All right, so let's get some practice with this. So, predict whether or not each of the following compounds is 1, soluble in water, and 2, soluble in an organic solvent. And I think actually I'm going to change this one slightly just so it's more familiar to us, since I haven't shown you yet what CH3 means. So with this one, you can apply what you've learned previously, in your previous classes, to figure out whether overall it's polar or nonpolar. Okay, so go ahead, pause the video, try this out, and we'll come back together and go through it in 3, 2, 1. Okay, so for A, C12H26, that has a whole bunch of carbons, a whole bunch of hydrogens, and nothing in there, no bonds that are polar that could possibly make the molecule overall polar. So this is an overall non-polar polar molecule, and so it's definitely not going to be soluble in water. Remember that water is super, super, super polar, and something will be soluble in water only, well, an organic compound will be soluble in water only if it is small and it has an O, an N, or an F that can hydrogen bond with the water. Okay, is this going to be soluble in an organic solvent? Well, an organic solvent is going to have carbons and probably hydrogens, and so it's going to be nonpolar enough such that it makes this able to mix with it. So the answer for this would be yes, it's soluble in an organic solvent. Okay, the next one, we could draw in our bond dipole and figure out overall if this is a polar molecule. So here I have the bond between carbon and oxygen is a polar bond. We definitely see an overall, that the molecule overall is polar since there's a separation of charge. If we think of this as a blanket, the blanket would be like hanging out around the oxygen instead of around the carbons and hydrogens. And so this is a polar molecule. It would be soluble in water because number one, it's polar. Number two, it's relatively small. And number three, it has an oxygen that's able to hydrogen bond with the water. So would it be soluble in water? The answer is yes. Okay, would it be soluble in an organic solvent? Now, you might have been tempted, and I'm sure that many of you made this mistake, which is why I like to go through this. You might have been tempted to think, well, okay, it's polar, and so if it's soluble in water, then it's not going to be soluble in something that has anything that's like non-polar that's part of it. But it actually is going to be soluble in an organic solvent because the organic solvent is non-polar enough that it's able to mix with the non-polar enough part of the this is called formaldehyde, but of this molecule, in order for them to be soluble. So, again, when you are thinking about whether organic compounds are soluble in organic solvents, the answer is almost always yes. And I'm not going to make the distinction between like when it is and when it isn't. At least not until later when we get a lot more practice looking at intermolecular forces and thinking about solubility of organic compounds. Okay, so to wrap up this video, I want to go very, very briefly over acids and bases, which is just like completely changing directions. So think of this as like almost a new video, but it won't take very long, which is why I wanted to include it here. So an acid is something that is able to donate, or in other words, lose an H+. So that can donate, so in parentheses, lose an H+. And an H+ is also called a proton. All right, a base is something that can accept, or in other words, gain an H+. And we're going to use the terms H+ and protons like synonymously, you know, they mean the same thing. So I'm going to write that here, that H+ is also called a proton. Okay, so if we're looking at an acid-base reaction like this, it's important that we're able to tell what's the acid and what's the base. Because in organic chemistry, we're also going to have certain organic compounds that are acids or bases. Okay, so with this, what we look at is, to find the acid, we look at what has lost a proton. To find the base, we look at what has gained a proton. So HCl has become Cl- by losing a proton. Okay, so I'll write that out, that HCl has lost an H+, it's lost a proton to become Cl-. Therefore, what that means is that in this reaction, HCl is the acid. We also know that acids will always react with bases in an acid-base reaction, so once we figure out one, then we don't really need to figure out the other, because like it's just whatever the other thing is, but let's just do it anyway. So in this, water has become H3O+, and to become H3O+, it had to gain a proton, or to accept a proton, and that makes it a base. So H2O has gained a proton to become H3O+, which means that H2O is a base. Now, I want to make the distinction that that is in this reaction. So in this reaction, RXN, standing for reaction. And that is because as you probably learned in your 121 class, and as we are going to see later when we go through some reactions in this class, we can see water, sometimes it acts like an acid and sometimes it acts like a base, depending on what it's with. So I'm making the distinction that HCl being an acid and H2O being a base, that is just specifically for this reaction. All right, so that's it. That concludes our review of 121. Now, I know that you've seen there's a whole bunch more in 121 that you did, but these concepts that we've gone through are the most pertinent ones for our class in 131 moving forward. All right, I will see you next time. Bye-bye. Bye-bye now. Bye-bye. I feel like Barbie in Toy Story. See you later.